Okay, so just to finish up on metallic bonds, we were talking about, or ionic bonds, excuse me. It's possible, for example, if you look at aluminum here, it has one, two, three of the valence electrons. Uh, Both of the oxygen atoms have six, so they have two unpaired valence electrons that need an electron. And so if you try to combine aluminum, aluminum can give two of its bonds, and that makes the oxygen happy and completes, fills its outside layer, so it has eight. But that doesn't come out even. You still have this one left over from this aluminum. Another aluminum atom can do the same thing. It can give two of its electrons to an oxygen atom, which makes the oxygen full, and it's out, and therefore a happy atom, an ion. But they both have an extra one left over. So if they give, each one of them gives their extra one to a third oxygen atom, then it will come out neutral, and so everybody will be happy. The aluminum will have lost all of its electrons, and the oxygens will all be full. And so in order to do that, we say aluminum has a +3 charge, oxygen has a -2 charge. If we have two aluminums, that gives a total of 6 positive charges, and we have 3 oxygens, which gives us a total of 6 negative charges, then it will come out evenly where all the oxygens are full and all the aluminums have lost their outside layer, so their next layer is full, and they're all happy ions, and therefore can combine and make an ionic compound. All right, and so that's the reason why when you make different compounds, they have different number of atoms in the compound. It depends on how much it takes to make it neutral. Okay, because the whole compound must be neutral. Now, the next thing we're going to talk about are metallic bonds. In a metallic bond, we look at these and we have the nucleus, which is positive, and the inside layers of electrons, which still give it a positive charge, are arranged in kind of like a lattice. They're spread out every so often, and they're pretty fixed. They don't move around very much. But that outside layer of electrons can move around, and we say are fluid because they can kind of move around from one electron to another. We could kind of like it when someone goes to the park and some people want to watch their kids. Metals aren't like that. Their electrons can kind of wander around. As long as there's still electrons around them, they don't really care if it's their electrons or someone else's electrons. And so they don't mind if these electrons go wandering off as long as they still have some electrons around them. Okay, and since the electrons are fairly fluid and can move around inside that, that gives them some of the properties that metals have. Okay, since electricity is just a flow of electrons, since these electrons flow easily between atom to atom, they don't hold on to them real tightly, then it's very easy for electric current to flow through these. And so these are very good conductors of electricity. Okay, and the reason metals are such good conductors is because their electrons just kind of float around on their own, doing what they want. Okay. Besides electricity, heat is also transferred by the motion of the electrons, and since they move around easily, it's easy for once one electron gets heated up, it hits the other one and passes it on very well because they're very movable, bounceable, roundable electrons. So it's passed on very well, and so heat can travel through it. And that's why if you grab one end, if you heat one end of a rod or say a handle, um, of a skillet, if you touch the other handle over here, it's going to be hot pretty quickly because the electrons move so well that it spreads that heat energy, which makes these electrons move faster, and they hit these and start moving faster, and they hit these and start moving faster, and next thing you know, over here, it's very hot very quickly. Okay, and so they very well conduct heat and electricity because their movement of these electrons allow that to happen. Also, in related to that, if these electrons are hit by light, say a light ray comes in and hits them, okay, they will begin to vibrate, and very often, since they easily vibrate, and since they vibrate at the same frequency, this will cause the light to reflect. And so most metals tend to be shiny. Okay, we say it's one of the characteristics. Shiny, which really what we mean when we say shiny is it reflects light. And so it reflects light once again because of the motion of those electrons. They move very easily and they move at the same frequency as the light that hits them, and therefore it causes it to be bounced back out. Okay? Now, the last thing we talked about metals the other day, we said something about them being malleable, which means you can hammer them out into sheets. And we said they are ductile, which means you can stretch them out and make wires and things out of them. Okay, and that also has to do with the electrons. Since the electrons are fairly fluid in there, the atoms can move about more. Now, they don't move around on their own. Metal looks fairly solid, but if you start hammering it, unlike a crystal, which is very locked into place, crystals are very, you've got atoms here and here, and they're locked into place, and they will not move very much. If you were to hit it, it just shatters into little pieces and whatever. On these, since the electrons are kind of moving around in here anyhow, it allows them to be flattened or be stretched out into wires without losing their shape, because this fluidness based on these electrons going through here allow them to slide into place and not be destroyed, okay? Whereas if you did a salt crystal and you hit it with a hammer, it's just going to break into, shatter into little pieces, okay? A piece of metal, on the other hand, will slide into a different shape and stay intact or stay into one piece, okay, which allows us to mold metals to whatever kind of shape we want to do. All right. Now, a lot of times we will have metals of two different kinds joined together, okay? And if we do that, that is called an alloy. All right? An alloy is just a mixture of two or more metals. Okay. And the purpose of an alloy is to combine some of these characteristics. They're both going to have the same lattice structure and everything, allows us to do this, but we can combine different ones to get different properties. For example, pure gold is not very strong. If it were to get bumped or hit, it would change its shape, it would get deformed, and it would not, for example, make a very good ring. All right. So instead, we add other metals to it to make it stronger, and yet still mostly gold, so that it keeps the color. Things like white gold is gold plus an element called palladium, okay, which comes from the word pallid or pale, and so it lightens up the color of the gold, and so it's called white gold. But it's actually a mixture, an alloy of gold plus another metal element called palladium. Bronze is a very common one. Copper plus tin. The Bronze Age was when people first made that. The brass is made with copper plus zinc. Okay, a lot of our coins, for example, our nickel is not made out of very much nickel, but it's a nickel and combinations of other coins. Pennies are no longer just copper; they are copper with mostly zinc on the inside because it's cheaper that way. And otherwise, if they made them out of copper, it would cost more than a penny to make them. But anyhow, those are all alloys. Steel is an alloy; it's iron plus some other type of element. A lot of times carbon is the most common one for stainless steel, but there's magnesium. They can add things like titanium stuff to make very strong things for like rocket motors and things like that that need extremely strong alloys. But those are alloys, and those are all metallic bonds. Type of bond. We've got ionic, which make crystals, which are very rigid, usually making pretty minerals, things like that. We have metallics and metals that have free-forming electrons, allow them to bend and change shape. The third one is covalent bonds. Okay, co means to share, so they're sharing valence electrons, so they're called covalent bonds. And so these are atoms that are held together in a compound by sharing their electrons. And this is most common in nonmetals or elements that want to attract electrons. They both want to attract the electrons. So instead of like with an ionic bond, where one grabs the electron, the other one loses it, they tend to share it. Okay. Some examples are these are H2. Hydrogen is what we call a diatomic gas. That means there's always two atoms stuck together. Oxygen is also like this. Fluorine, bromine, iodine. There are some others. Okay. Carbon combined to itself in different ways. So you could have 4 carbons joined to each other. Diamonds, and depending on how they combine together, they can make graphite, which is pencil lead, or diamonds. Whatever else has to do with the heat and pressure they're combined to. Other ones like NH3, which is ammonia, Okay, ammonia, notice it's nitrogen and 3 hydrogens, and these are all gases and non-metal-y type of things. If you remember, hydrogen has a fairly high electronegativity. It wants to hang on to its electrons. H2O, which is, of course, water, and carbon dioxide is also another very important one to us. All of these are covalent bonds because they're either atoms bonding with themselves, which means they have the same electronegativity and they both want to equally hold on to the electrons, or they're nonmetals that all have fairly high electronegativities and want to hang on to those. All right. For example, if we look at hydrogen and do the Lewis dot, we know that hydrogen has only one electron in its outer thing. And if it wants to combine with another hydrogen, all right, it has one. Now, hydrogen only has the one orbital around it, usually one proton, and therefore it has one, it wants to fill that up and have two. Well, if you have two hydrogens, they can combine with each other rather than one taking it away, and they just share those two electrons. So they share, and this hydrogen and that hydrogen feel like they both have access to two electrons because they're sharing with each other. And instead of just doing two dots, we usually just draw a line right there, and that shows that we have a covalent bond between those two hydrogens. Okay. Now, in oxygen, we also have a similar thing. We have 2 and 2, but then we have 1 and 1. So it has a total of 6 valence electrons. Okay, and if we add hydrogen, it can share this one, and that makes 1. Okay, and we have to add another hydrogen, so this one can share. And now they share those, and oxygen feels like it has access to 8, and therefore it's happy. And each of the hydrogens feels like it has access to 2 electrons, and so that makes it happy. And so in cases of the same element or nonmetals, they may just end up sharing these electrons. Now, it's possible to have that carbon could be bonded to 2 hydrogens, and it could be double bonded to an oxygen because oxygen tends to have 2 bonds that it wants to have. So carbon would be happy because it's sharing 4 pairs of electrons, is 8. The hydrogens are happy because they're sharing 2 electrons, and the oxygen would have 4 up here, and then here's 4 more electrons it has access to, so it would be happy. This would be a double bond. It is possible for some elements to have a triple bond between them. Okay, and so you see single, double, triple bond. We usually just represent it with these lines, but there are all types of covalent bonds. So let me go back just a second here. Now, if we have 2 elements of the same one, okay, such as the 2 hydrogens here, okay, their electronegativity, how much they want to hang on to that electron, are exactly the same. So this one's going to pull on the electrons just as much as that one pulls on the electrons, and so they are going to share equally. All right, and so this is called a nonpolar covalent bond. Okay, a nonpolar covalent. Sorry, my R didn't get on there. Now, on the other hand, if we look at oxygen and hydrogens, oxygen is more electronegative, and it really wants to pull those things. And it's kind of like if you have a bully, a big kid and 2 little kids sharing toys in the playground. If the big one is stronger and it wants to share them, then that child is going to have the share the toys a lot more of the time than the little ones are. And the same thing happens here. Oxygen is your big bully, if you will. It has a stronger pull on the electrons. So most of the time, these electrons are over here by the oxygen atom. So it has more negative charge. And so we say this part, the oxygen side, would be the negative charge of it. The hydrogens, being small, don't get to hang on to the electrons very much. They get them occasionally just to keep them hanging on, but not very much. So this side tends to be positive. And so we have a poles, positive and negative poles, if you will. You have a water molecule, but the oxygen side of the water molecule is negative, and the hydrogen side is positive. Okay, this is called a polar covalent bond. Okay, because some of the atoms are pulling on the electrons more of the time. They become negatively charged, and the smaller ones, or the ones that don't have as much pull, tend to become positive. All right. These on